I would recommend meeting.
All right, guys, we'll go ahead and get started. I'm going to offer one more sort of informal tutoring on Wednesday at 5 to 6 in McLean 174. So that's where we have the 2A lab, so in that room. So I'll be there if you have any questions. If you haven't asked anybody yet and you're still unsure about anything, you just come in, say, I don't understand anything with energy. Okay, we could start there, and I can, just go. I don't have anything planned, so it's whatever type of questions you guys bring, I'll go over for that time. All right, let's see. I have just a little. Yeah.
Do you have normal, weekly tutoring times on Zoom or anything at all?
I have my weekly office hours. They're listed on Canvas. So those are 3 to 4:30 every Tuesday and Thursday. And then Wednesday, noon to 1. So I'm in my office hours, throughout the whole week. So if you have questions normally, you can stop by my Zoom office hours. They're, you'll just put you in a list of whoever shows up first. I'll help you guys out. Let's see. Yeah. So I'm going to finish out this chapter on rotational motion today, and then we'll do just a, sort of a grand summary of everything we've gone over in the class so far, and that will be on the exam. All right. So we stopped last time looking at sort of a picture like this, and I did a little demo with some water, and I did a different demo with the tennis ball. And I was saying that looking at a picture like this, the orange arrow, that's the inward force. That's the force of tension of, if I take this ball and I start rotating it, I could do it sideways like this, or sort of over my head. If I get it to go over my head like that. There's a force holding it to form this sort of circular motion. That's that orange arrow. Whereas the green arrow up there, that's the direction the ball wants to move in. That's its velocity. And I told you guys, the reason that it's sort of always turning is that it's being forced, and then it turns just a little bit, and then now it's being forced a little bit more, and then it just keeps turning. And I did sort of a very rough 2 or 3 turns. You can imagine if it's a constant force, we have this nice, perfect sort of round circle. Objects normally want to travel in a straight line. That was from Newton's first law. Let me put that up on the board. I'll refer to it one more time later. So Newton's first law was you could say it's like the inertia law. Objects at rest tend to stay at rest. Objects at rest tend to stay at rest. Rest tend to stay at rest. And the other half was objects in motion tend to stay in motion. Last time, though, objects in motion. Last time I said there was just a slight little thing I was leaving out. First time we went over this. Objects in linear motion or straight line motion. Objects only want to move in straight lines all the time. I could say straight line motion. And that explains this, green arrow up here of this thing, wanting to move in a straight line. And then I also did like demo, I sort of like would let go of the ball. Imagine if I cut the string, which direction would the ball travel? So we've gone over this idea of this inward centripetal force. There's also what's called an apparent force. And you might be familiar with, the term like I put objects in a centrifuge or a centrifugal force. That's what we're going to see as an apparent force. Right now, I just went over centripetal forces. So make sure I'm going to refer to both of them right here. So this one right here I just went over, centripetal, that means pointing towards the center of the circular motion. So that one right here I'm going to say as center seeking. That's this, the tension or whatever is holding that rotating object, whatever is making it turn. So in this case, it is a string, sort of constantly pulling it towards the middle. I have another example up here. So I have this little plexiglass dish, a little steel ball, and a cutout of circle. And on one side, if I do just the circle, okay, that looks good. If I do just the circle and I give it some, a little bit of a push, it will travel in a circle. It's traveling in, and then it gives up. So there is this sort of external force trying to push it in this circular motion. And that's this plexiglass. It's constantly pushing it in this circular form. And as soon as that force is no longer there, the object will travel in a straight line. And that's this other side I have over here. A portion of it cut out. So if I give it a sort of some initial velocity over here, let's go like faster than that, it will escape and then travel in a straight line from wherever it's no longer being forced to travel in this circle. So as this tennis ball is something, pulling it inward, this plexiglass is something pushing it inward, this sort of a barrier. Okay. But then we may talk about some sort of, or you may hear about some sort of outward, pointing force. You may have heard the term centrifugal force that will push an object outward. And this is from, experience. If you guys have ever been on like a merry-go-round or one of those like theme park rides where you stand against the wall, it feels like you're being pushed out against the wall, right? It's spinning you. It feels like you're being pushed outward. But you're not. That is going to be an apparent force. This centrifugal, this one right here, is apparent, and which basically means it's not real. It just feels like it's real. When you or you're sort of looking at it from a different point of view. I'll explain more in a bit. Apparent force. Or I could say not a real force. All right, and the reason that we have this is going to be from Newton's first law, this one right here. And I'll sort of draw up a little picture to help this explanation. So let's say we have something like, I don't know, we have this ball on a string example like you use for this whole chapter. I have this ball on a string, and it's rotating, and I go sort of piece by piece. Let's draw this out piece by piece. And we'll label the forces this time. So previously I told you that we're doing accelerations. Let's do the forces. So say we have this object or this ball or that ball over there or some sort of wheel. In this case, we'll say it's a ball. And I give it a push. Newton's first law says it wants to move in a straight line. So it wants to do this. It wants to move in a straight line and end up, let's say right here. So that's where it wants to end up. All right, this very conceptual sort of picture I'm drawing. All right, Newton's first law says it wants to move in a line. But let's pin this thing down with a string or cable. And let's say now it's connected by a cable like that. And it's pinned down, it can't move away from, this length of string that it's on. All right, so I give it a push this time, and you can see what it wants to do. It wants to go straight, and it wants to end up right there over a period of time. But it can't do that. Instead, is being forced to turn like that. Okay? And so where it actually ends up is going to be right here. All right, and what is making it turn that direction? It's going to be the centripetal force, the inward pointing force. So we have that centripetal force from the string. Let's make it like bright blue. We have that force. It's pointing in. It's pointing that way. It's making it turn, and it's pointing that way. It's still making it turn, and we have that. Nope. Let me do this. That centripetal force pointing inward, and that's from the string. Right? It's still connected to the string. No, I don't want blue. I want the black one. All right, so it's still connected to the string, and it has been made to turn because it's pinned down on the string. And so now it ends up in that, underneath position. Right? And what we're feeling when we're in that amusement park ride or we're on that merry-go-round, we feel it trying to force us outward. That's not a force outward. That is us trying to move in that straight line. So you see this sort of dotted line connection I have right here. See the difference between where it wanted to be originally versus where it ended up. That difference right there is what we experience when we're forced against the wall on that, right? I don't know what it's called. It's probably like the twister or something generic like that. So the difference between these two, and because it's following, all objects are going to be following Newton's first law, that is that apparent force. So we have, let me start labeling some things. We have this one over here is centripetal. Centripetal force is the one pointing inward, and that apparent force, outward, that is not a real force. That is what is commonly just called centrifugal. Centrifugal force. That's an apparent force, and it's not real. And a way it can prove, yeah.
So why do we call it a force if it's not a real force?
It just is, I think it's because it feels so significant when we're in that situation, when we're in the, that ride, or we have experiments and it appears that something's trying to move outward. We are allowed to call it an apparent force. So that's why I'm making sure to include apparent force every time I reference it. So I'm just telling you that people might mistake it as a force.
Okay.
So, yeah. So I'm just constantly reminding you each time I write it up here that's not a real force. And I can prove it's not a real force because let's say I have this situation and I have that ball and a string, and we've all learned like summing forces and all that so far. We have a force pointing inward, that's real. That we know that's the centripetal is inward. And let's say we wanted to figure out if the centrifugal was real or not. So if I was to start rotating this thing, and let's say there was no centripetal force anymore. That's the blue one. What direction would the ball be sort of going then? Right. So in my picture here, if the blue force disappeared, say I cut the string, then if the red one was real, it would then sort of curve back and go outward, right? But that doesn't happen. If I cut the string and let it go, we see that there's no curving back, there's no outward force. There's only tangential velocity. And so just by doing that, just by doing my sort of demo up here with the plexiglass, so if we had the same sort of thing, the walls of the plexiglass are pointing, trying to force it inward. If there was this outward push, then as soon as it leaves, it would turn that way. But we don't see that, right? We see something else. Nothing is forcing this thing outward. So we have all proven together, just sort of observations, that there is no outward push. All right. Okay, next up, this chapter had a lot of gravitation and, center mass stuff. I thought it was a bit too unrelated at the moment. I do want to cover a little bit, just so we can, see some of the cool things that are in there. Let's look at, we've been doing, like, I have this small example, a ball and a string. I have this thing moving in a circle. I had a wheel the other day. Let's think about some big examples, much bigger. Let's look at maybe the orbits of something moving around the Earth. So when Amazon and SpaceX, they're all trying to go to space. What does it mean when all of these, people are going to space? What are they actually doing? Are they going up and then coming back down? What's actually happening? So I'll tell you maybe a bit more detail about orbit. So when we say orbit, that's something that is quickly moving around the Earth. So let's imagine we have the Earth and just make it a big old ball. Like that. And we have a very large, very powerful cannon. And we put it on the top of a mountain, even. We point it completely horizontally. We've done a problem like that before. Just something horizontal. It's eventually going to fall down, right? So let's have a cannon up here. It's going to fire something horizontally. So if it, comes out, it's going to arc downward and then hit the surface, right? So arc downward and then hit the surface. What if I, shoot the cannonball out faster? Okay, well, it's going to come out and it's going to hit the other side of the country. This is me, launching a mortar shell or something. Okay, if I launch it a little bit faster, now it's going to hit another country. I could keep doing this more and more and more and more and more until I launch this projectile just completely horizontally, completely flat. It's not going up at all. Until this thing will go all the way around the Earth. Then all I have to do is move the cannon out of the way, and that thing will keep going around and around the Earth until something else acts on it for it to slow down. So this is orbit. This is what all satellites, space stations, telescopes in space, that's what they're all doing. They're orbiting the Earth. They're just moving very, very quickly in this big circle. All right, so that means they have a lot of need for what we're talking about with rotational motion, and you think about tangential velocity, rotational velocity, things like that. Now, if, say, something's doing this, which way is down? They're going out, and for those 3 test fires, they all eventually hit the ground. But for that last one, which way is down? Down is continuously changing for them, right? It's the Earth is sort of avoiding them as they travel all the way around. So the people in the spaceship itself, satellites, they all sort of just float there with a some weightlessness. So it's apparent weightlessness. So that's when you see things, floating in space, people in the space station. They and the space station are both traveling very quickly, and basically the Earth is avoiding them as they keep trying to fall down and hit the Earth, but they're just traveling too fast to reach the ground. All right. Something that, let's see. People in, these situations, the space station, they don't have an ability to actually move around the cabin. They have to push off of the sides of the walls. They have this apparent weightlessness. And so there's no more force of gravity holding them down. So after a lot of years, they've figured out that people with this job, they experience sort of calcium deficiency and muscle reduction because they don't live under the weight of Earth's gravity anymore. And so they need to exercise daily. How do they exercise? They need to strain their muscles. They need to strain their bones. They can only do that with force applied. And so they have to actually tether themselves down to the ground of the spaceship, or tether themselves to a bike, because otherwise they'll kick off of it and float away from it. So they have a very strict, exercise routine up in space. Otherwise they'll come back down to Earth and not even be able to walk for a month, because they don't have enough, experience with, restricting, working in this sort of large force of gravity. And, one solution to this, it's also on topic, is instead of, strapping people down, we can build a specific type of space station. We could build one that has artificial gravity. How do we do that? Well, we could have a big sort of round donut-shaped space station that spins pretty quickly. This spin at a specific speed. So if we have one, this sort of concept art, and it was sort of thought up, a long time ago, when we first started space travel. So right there you see that's 2 or 3 floors. And this is going to be a huge space station that is spinning. And all of the people, all of the objects in it are trying to move in a straight line. But the space station keeps turning, and so it feels like they're being forced into the ground of the space station. So that's how we can create artificial gravity, kind of like this. This is from a movie. Does anyone know what movie?
2001, Space Odyssey.
Yeah, you got it. So, maybe in, a couple dozen years, there might be one like this. All right. And with that, go like that. I'm going to go over a little bit of review for the exam. All right, so first start out exam 1 is going to be on Thursday, we'll say, you can use any type of calculator, I don't care. I'll just say need a calculator. You later. And we're also going to need a Scantron. What was the number? It was 882E or something like that. Scantron. It's the green. It's the green one. It's the basic one from the bookstore. Well, I'm gonna need one. Calculator. That. I'm going to say that I will provide formula sheets for you guys. So you're going to use the ones that I give you. Yeah. Yeah.
Oh, we cannot bring any type of study guide with us.
Study guide? No. So, right, I figured I will give everyone all of the equations that you need for the exam. That way everyone has the same material, everyone is on the same footing. And I will give you, basically all of the equations we have so far. It'll be sort of, I'm not going to say like what each variable is. It's up to you guys to know what the equations are for. But I'll have them, arranged nicely. Sound good? Okay, yeah.
Can you post the formula, like as a Word doc or something on Canvas, or do you want to give it to like on the day of? Does that make sense? Like,
yeah.
Teachers like upload the formulas and stuff, so you could go over them.
We'll probably go over them today, right now. So I'm gonna just have it as like the front sheet. You guys can use that as your formula sheet. All right. That and the material for the exam is going to be from chapter 1 all the way to chapter 6, I believe. Yeah.
Are the questions similar to the questions on the quizzes, or the more?
I'll say more similar to the quizzes, because I've written the quizzes. They probably, so I gave you guys a good amount of time for the quizzes, so maybe a bit less intense as the quizzes. That makes sense. You guys gotta do like a lot of material in an hour, and so I'll say kind of like the quizzes, more like the quizzes. Yeah.
So we'll have like true and false too and stuff?
You'll probably have some of those. Maybe. Yeah.
Is there free response?
Free response? There's going to be a good portion of that. I'm going to say roughly half. Yeah.
How many questions?
Between 15 and 20. This is very general. Okay. All right. Let's see. What else? Is any like more general questions or things like that? So we're going to go into kind of more detail right now. All right. Chapter 1 was about units, vectors, and trigonometry review. So let's write that down. Chapter 1, units, trig, and vectors. What did we do with units? Well, how to convert units, going from one thing to another. Not just, some vague, feet to, kilometers, things like that. I mean, also, what does a kilometer mean? Maybe kilometers to meters to centimeters. How do you do that? So I'll just put up my examples. Feet to kilometers. How do you do that? Also, what do kilometers, meters, centimeters mean? You should know that. Kilometers, meters, centimeters. How do you go from one to the other? Trig review? Well, that's, yeah.
What would be given the conversions?
If it's something vague, if it's something like this up here, then I'll give you the one that is least obvious. But going from kilometers to meters, you should know that. Okay. Trig and vectors were kind of together. So vectors, it's like that's vector A, and I want to add that to vector B. Okay, typically you'll be given an angle and a magnitude, a size of the vector. How do I add these two things together? Also, on a related note, so I'd say up here, that's vectors. How do I add those? This sort of bottom note down here, that's trig review. So that is breaking a vector up into its components, which is a sub x, a sub y. Can you do that? Knowing how to do that quickly will save you a lot of time on this test. I'll tell you right now. We also will need an angle. So these two things on the right, they're related. And we're going to make a lot of use of SOHCAHTOA. So we use that to find the components. You guys got this, or you want me to go in a bit more on these trig functions? More? Okay. So the first one right here. Sine of the angle is, so SOH, that's opposite over hypotenuse. Or I guess I'll use the example vector I have up here. Then the middle term right here, that is cosine. Cosine of the angle is AH, so adjacent over hypotenuse. So for this angle that is right here, the adjacent side is A sub x. And the last one, let's do TOA. That is tangent. Tangent is opposite over adjacent. Good. I'll say if you can do this quickly, if you know how to work through this quickly, as you've probably seen, that's where we mostly start all of our problems, was with some sort of trig relation. Okay? All right. Next up, we had, what else was in this chapter? There were sig figs, right? Significant figures. So I just had like one page of rules that I wrote out. How many significant figures is in, I don't know, can you do that right now? How many is in that one? 3, yeah. How about that? There's still 3, right? And that? 1. Yeah.
How was it 3 in the first one again?
There are 3 in the first one. We ignore the leading zeros. Then we say if there's a decimal point, we accept all of the trailing zeros. So I'd say if you got that, or if you didn't get that, you can go back to those sig fig rules. All right. What else? I think that was it for this first chapter. Scientific notation. I don't really go over that too much. Trig, vectors. Yeah. All right, next chapter. Chapter 2. I'll put it up here. That was motion in one dimension. What did we go over? That's when I just sort of introduced displacement and distance and velocity and acceleration. So I just was introducing the concept of those things. So what were some of my examples? I did distance versus displacement. So what was the difference between the two? Distance is how far you've traveled in total. The displacement is only taking account your start and stop position. So that was us looking at positions, right? displacement. Okay, then I introduced velocity, which is just the displacement over time. I did average velocity and instantaneous velocity. So we had V average delta T, like that. Same sort of thing for acceleration. Acceleration. That was velocity over time. Sorry, change of velocity. And we can find the average acceleration. All right. Then I said that if we have some sort of constant acceleration, so I said for a constant acceleration, we can use these equations, and I just sort of laid on these kinematic equations that have been a nightmare since then. So I originally gave you 5. I'm just going to list out the first 3. Come on. Decided it wanted to freeze. Okay. So we have, for constant acceleration, we have the kinematic equations of motion. That one, and then we have this one. Okay. Okay. No. Program. Okay. So, yeah.
Of the original equations, there was one that she derived from the last one. Will that one be given as well, or?
Yeah. Yeah. So I'll just put all of them up here. So we had or I had B. No, I want to do this. So there's that one, and I believe the other one I had was 1/2 B naught. Yeah. Okay, so we had these, and we continue to have those. That's gonna, yeah.
Are you gonna go any practice problems like this?
Today, right now, I don't think I will.
Okay.
Let's see.
I'm saying that if you want practice problems, you
Yeah, if you want to get like a specific problem, you can go to my office hours or to the tutoring thing. I even have office hours on that day, or on the test day. Yeah. Right, so that's just going to stay up there for right now. The next chapter was chapter 2. Yeah.
Is this what X in the second one?
This one?
Yeah.
So I may have written it like this in
Oh, change.
a different version. I had written it like this. Right? And so what I'm doing, I subtract that over. I have x minus x naught. And that is delta x, so change in position. And so some formulas might just start you out by saying delta x equals that. Right? Okay. Okay. Chapter 2 was largely the same as chapter, sorry, this is chapter 2. Chapter 3 was largely the same as chapter 2. Chapter 3, motion in 2 dimensions. All I did in chapter 2 was explain that you can separate things into 2 different types of motion. So we have, or we're now going to use those same kinematics, but in 2 different component forms. So say I have, I don't know, we'll just do the basic projectile type of thing. Right. So we have something that is moving to the right, and it's also going up and then back down, right? So trying to wrap your head around splitting up the components in a problem like this. This is basically a problem that has a ball going up to this height and then falling back down to the ground. So that's the vertical component. How is the object moving in that manner? And then also, how is the object moving horizontally? So this is vertical. And how is the object moving horizontally? It's going to move with a constant velocity. That way. I think I drew like way too many pictures or something back then. But we use the same kinematics, we just split it up into vertical. Do just the same. But now we label everything a bit more clear. So velocity, final velocity in the y direction is equal to the initial velocity in the y direction plus acceleration in the y direction times delta t. And then I continue. Instead of x, now it's delta y. T plus 1/2 squared, and then I'll just do this last one, y. So I would use these for the vertical motion only. Then I would have another list. It's the same exact list that I have over there. Except all of the terms are x, because it's something moving horizontally. So basically this, again, we have to label everything. V of x, V naught of x. Horizontal motion. Okay. Okay. That's not helpful. I'll go like this. All right. Okay. Chapter 3. Chapter 4 was, I think, Newton's laws of motion. Newton's laws, that's where he started talking about forces and summing up forces in different directions. So if you remember the first, second, and third law, what are they? Might be important to know. One of those three is this right here, the relationship between force, mass, and acceleration. that, and that. When I started just having like a box on a table and talking at it for an hour, we had me introducing forces and the free body diagrams we use so much. So we have an object or something on the table. Maybe I don't want to draw that all the time. Draw it just as a dot. What kind of forces are acting on this object? I'm just going to list them all out in this really easy to read diagram. If it's not easy for you to read, then maybe try a different technique in drawing it. So you should be able to just look at it and be like, that is that, that is that, that is that. I'm good to go. This should be a helpful tool later on in this next step. So right here, something that is just sitting there, not moving. It has its own weight, I call F of G. So that's the mass of the object times the acceleration of gravity downward. I'll just put it right here. And since it's not accelerating down or up, it's not moving at all, I can easily say that it's equal to the normal force, pointed upwards. Okay, so drawing these would be helpful when we sum the forces. That's usually our next step here. So we sum the forces, we look at the vertical forces. So this is just me like preparing, I'm saying I'm summing the vertical forces. I chant that to myself every time I start this problem. Summing the vertical forces. Then I list out everything moving up and down, or all of the forces pointing up or down. All of the ones pointing up are positive. In this case, that's the normal force. All of the vertical forces that are pointing down are negative. Okay. Then when I'm done, I've listed all of them. Maybe I have several more going up and down. Then I end this statement by saying all of the vertical forces are making the object move like this. So that's making the object of mass move in this way. And so for the case of my little, tablet holder right here, it's not accelerating up or down, so it's not moving in any way. And so this acceleration right here is 0. And I can solve later on for that. Summing vertical is also summing horizontal. It's the same thing. Summing the horizontal forces is equal to, and I look at my diagram, there's nothing. So there's nothing, I put 0. So that means that there's no forces, that means this object is not accelerating. That's like 0 equals this, so that means acceleration is 0. Yeah?
So for the vertical force, why did you say the acceleration was 0 when we have negative acceleration, which is gravity.
Right, we have negative acceleration for the gravity right here, trying to force it downward. The table is trying to force it upwards. But we're relating this to how is the object in total, how is it moving? So is it currently accelerating upwards? Is it on a string and I'm lifting it up at a certain acceleration? Or am I lowering it down at an acceleration? So that's what I mean right there. It's not accelerating currently up or down.
Okay. So let's say you had a string and you hung it from the end of the table.
Yeah.
Would the negative gravity acceleration be considered in that problem?
So if I was just to like hang it like this?
Yeah.
So still, and then it would turn into tension. Still, it's not moving, it's not accelerating up or down.
Okay.
If I was to slowly start, or start out slowly and then speed up, accelerating it downward, then that's its movement. Or this was like that elevator problem I brought up during class. But largely, this is what we did in forces. Drawing pictures, summing arrows, different directions. Okay. And the last two chapters I'll put up at once. Or maybe I'll go, we'll see. Chapter 5 was energy. So in this chapter, we talked about work and energy. What does work mean? So work was the ability for you to force something and make it move. So work was force over a distance. Okay. Then we talked about the types of energy that there are. Energy can't be created or destroyed. So there was a conservation of energy, what we covered. This is when I brought up potential energy, gravitational and elastic potential energy, right? So I like that. Go like this. Is mass of the object times mgh. I think I said delta y this time. It's just this displacement. We also have elastic potential energy. That one was 1/2 kx squared. Some random terms right there. What was k? What was this letter k representing? The spring constant, or the book might say it's the force constant, or something like that. So that is how strong the spring is. It depends on the material. And x, that is how far you compress or stretch the spring from its equilibrium position. Lastly, we had kinetic energy. That is just energy of a moving thing. Energy of a moving thing. One half mv squared. Yeah.
Just making sure these equations are given also.
Yeah. Yeah.
So on the potential energy of elastic, the x, does it change sign when you stretch or compress? Or does it not really matter?
Typically, yeah, it would be like whichever direction is given in the problem. So, you compress something down from its, you're going to the left, right, in this problem, you're compressing it. Or if you're, I don't know. Go like that, the mass is going to stretch the spring. Delta y. So typically, I'll say yeah.
Okay.
If you guys get the problem right, you're off by a sign. I will check for that.
I don't think the sign would change though, because it's squared,
True. Yeah.
so like, it'll never be negative.
For that one, yes. There's also an additional one I will put up here. Hooke's law. I want to remember that one. It was very brief. I don't know why they put it in this chapter. This is the force of a spring. I don't know why they didn't put it in Newton's laws. Minus kx. Okay, so like this, how does energy transfer from one thing to another? Like, imagine we had this ramp, I have a block, a certain mass, it's up a certain height. It will have gravitational potential energy, and typically the problem will say it starts at rest, so there's no kinetic energy. And then it'll be like, this is a frictionless ramp. How fast is it going at the bottom? So just remembering that the energy form transfers. It goes from one form into another form. Cool. Okay. And lastly, we have momentum. So we have momentum. That was just looking at the conservation of momentum. What does that mean? So that means looking at whatever type of interaction you have. You have me in a chair pushing someone else, or you have a collision of any type. The momentum before the interaction is going to be the same as the momentum after the interaction. And I'll just put up also a reminder what momentum was mass times velocity. Okay, and then I think the last type of thing we did here was look at the types of collisions, elastic, where things bounce off of each other, and inelastic, things stick together. And so I did like several types of little pictures that were little collisions. One mass go with certain initial velocity, hit another mass, then there'd be a collision. What's the momentum afterwards? That's what we would be finding out. But ultimately, we know there's always going to be a conservation of momentum. So the momentum over here on the initial side is equal to the momentum on the final side. This. Make it work. Yeah. Okay. All right, any other questions? Okay, so I will provide formula sheets. Make sure you bring your Scantron and calculators and your brain, I guess. All right, I'll see you guys on Thursday.
I didn't think you were